welcome back. We're flipping gears back to linear algebra this morning. And we're focusing to start again on the image concept for transforms. And again, this is the points you can get out of a linear transform, valid outputs in the output space. All right. I just want to recap briefly what we saw last class because we're going to turn that into a general approach momentarily. So if we have a linear transform that we've represented as a matrix, then one of the things that we know is the columns of that matrix represent vectors in the output space. So this 2, 1, 4, we actually get, if I talk about the linear transform, I get 2, 1, 4 times whatever my input x value is, and then plus negative 3, 1, 5 times my other input. So literally we get all possible linear combinations of that column vector 2, 1, 4 and that column vector negative 3, 1, 5. So that's what I have to build my outputs with, and so they are a nice spanning set for the image. With those, I can get everywhere in the image. We want to take it one step further, though, and go, OK, spanning sets are great, but they can be a little bit too big. I can have extra things in my spanning set that I don't really need, and that gets us back to the idea of the basis. A basis is a trimmed-down spanning set. It's a spanning set that has no redundancies. It's a spanning set that's linearly independent. And that's what we found in this case here, was that we had 3 vectors, and they were fine vectors. They were a spanning set, great. But there's some redundancy. That second vector was actually just a multiple of the first. So do we need it to actually cover the output space? We don't. We can get rid of it and just keep the other 2 vectors instead. And that gives us a basis. From there, we can get dimensionality, so we can figure out that even though these are 3-dimensional vectors, the image, the places we can reach with this transform only cover a plane, and that's worthwhile information. But we'd like a process for this that is a little more standardized, and so that's what we're going to go through today. What we will observe as a starting point to that is when we looked at this matrix here, we found that both vectors were needed. And when we look at the RREF, we see leading ones corresponding to those same columns. Now that's sort of silly because it's only a 2-element matrix, 2-column matrix. What we see, the 3-column matrix is a little more interesting. We just kept the first and last vectors because they made a linearly independent set. And conveniently, when we look at the RREF version of that same matrix, oh, look, we have the same linear independence in the first and third columns, and pointing to maybe we could throw away the second column. And that's what we're going to bottle up into an algorithm. This is going to be a process you'll have to memorize or apply and then practice this one here. If we're looking for specifically a basis of the image, we're basically looking to remove any redundant columns. Because we already have a spanning set with the columns. The columns are great, but maybe some of them are extra. We don't need them in terms of places we can reach, places the image can, places that we can reach with the image. And so when we get something like this, we're like, whoa, that's a 3-by-4 matrix, a little bit more complicated. How can we identify which columns are really required here to make a basis for where we're going in the output space? So just a quick reminder. The whole set, all the columns, 2, -1, 1, 6, 3, -3, and -1, -1, 1, and 2, -7, 7 are a spanning set for the image of L. We're just looking for that trimmed down version of a spanning set, the basis. We want to get rid of any redundant ones. All right. Quick note about the input and output space. Because these are 3-element vectors, that means that R3 is our output space. We're building 3-dimensional vectors, linear combinations of them. And because we have 4 columns, that indicates that we have R4 is the input dimension. If we we're actually doing this transform, we'd have this times x plus this times y plus this times z plus this times whatever the fourth w input value was. All right. Now, before we crack through this, let me just pause there. That was a lot of review of things that are a little more abstract and stuff we have been doing recently. So any questions before we dive into the actual process? Please.
It's like, in this case, we're finding the image, like instead of like directly computing all the possible values that match the target set, we're finding it by finding the basis. So we can use the basis vectors to make all the vectors
In the image.
that are in the target set that are reached by the input set.
Exactly. So let me just paraphrase that. So when we talk about the image, it's a concept. We very rarely get a formula for the image. Instead, we get the building blocks that could be used to make it. And that's exactly what this basis would be. A spanning set is also a perfectly good way to make a collection of vectors. We say, I'm allowed to make any linear combination building with these building blocks. The basis is just a nice trim down, has other nice properties to it. There's uniqueness and some other stuff that comes with that. But yeah, we're looking for, what can I use to build the image? Perfect. Any other concept questions? If you're like, why, what? All right, then let's go through the algorithm. So the nice thing is, you've done this before. The process here, step one, is put this matrix into RREF. So we're going to do our usual row operations and get a row-reduced version of A. So what does that mean? We want, ideally, to have a 1 in the top left corner at the next stage. Well, we conveniently have a 1 already in our first column, so we're just going to keep row 3 to start and put it first. And let's do one operation while we're here. Let's take row 1 plus 2 row 2s. What that'll do is give me a 0 in the output value for that column there. This plus 2 times that is going to be another 0. That plus 2 times that is -3. That plus 2 times that is -14, -12. And let's just keep row 2 as is. Like so. It's nicer than row 1. And again, different people can make different choices at this stage, totally fine. The RREF will be the same for everybody if none of us made mistakes along the way. All right, angle this down a little bit. So we are pretty okay with row 3 right now, or I guess row 1 in the new matrix. So let's keep it as is, 1 minus 3, 1, 7. The zeros are fine, keep them, so that's row 2. And minus 3, oh, actually let's divide that by -3. Get some slightly nicer numbers, 1 and 4. And then I think it makes sense to take row 1 and row 3 and add them. And actually, yeah, it's going to give us some stuff here. 0. Oh, wait, it's a 0. That's it. All right. Alrighty. Last but not least, we're just going to trim up the other part of the last condition for RREF. We have leading 1s in every column. So there's a leading 1 here. There's a leading 1. Everything before the 1s are 0s. That's what the leading 1 is. And the last column is all 0s. That's totally fine. That happens sometimes. As long as there's no anything but 1s, we're good. The only thing that's standing out right now is I need to have 0s above all the leading 1s as well. So I want to clean off this column. So we can keep row 1. Row 1 minus row 2 is what we want here. That'll be no change, 0, and then 3. 1 minus 3, 0, 3. And then row 2 is lovely by itself. Row 3 is lovely. 4, 0. And that is now in reduced row echelon form, RREF. Let me know if you notice an error in there. I hope that's right. I think that's right. And once it is, we have this lovely approach afterwards that says you just have to look at that matrix, look for the leading 1s, and go back to the original matrix and keep those columns. Those are a set of linearly independent vectors that also span the whole space. So in this case here, we can go straight to the image of L has a basis of just two vectors. Two vectors, and it's those two matching leading ones, 2, -1, 1, and -1, -1, 1. So just a little tag on to the RREF process. We just interpret the results now. All right. Now you might be wondering, why? How does this work? Why does that make any sense? Well, first off, let's just take a quick note that the leading one columns are linearly independent, because if you think about components, this thing has an x component that's going that way. This thing has a y component that's going that way. Those have to be linearly independent. They're going in fundamentally different directions. So the columns leading ones always have, well, there are basis vectors, right? 1, 0, 0, 0, 1, 0. They're the simplest, most atomic basis vectors we can get for a space. The other ones, the other two columns, almost by definition, are multiples of the earlier ones. So this one here is just -3 times the first one. I don't need that -3, 0, 0 column because I have 1, 0, 0. I have the simpler version. This one here, it has numbers in the first two rows. Well, I can make a linear combination of the columns I picked to get 3, 4. I take 3 of this column plus 4 of that column, and I have that. So the columns without leading ones are redundant. They are linear combinations of the previous columns. Sorry, they're in there, yeah.
Why can't we just use like linear independent, like the 1 and the 0, 1 vectors instead of like the actual like non-RREF vectors there?
Sorry, can you say that again? Why?
Like, why can't we just like take them from the columns with the ones in them instead of like having to like go back to the original vector and take those ones?
Sorry, I think we are going back, because we do say that the linear combination that is a basis is these things. We don't say it's these. Are you saying why isn't it these ones? Oh, yeah, fair. Because some things get transformed when we do RREF and some things don't. If you take a look at the span of these vectors, you notice there is a z component, right? Whereas in here, if I took these two vectors in the RREF form, there's no z, and you're like, wait a minute, we just wiped out the z. So the RREF changes the directions we go in. What it doesn't do is change the dimensionality and some other things. We're talking about that in a second. But yeah, by the time we've row reduced echelon, we've changed something. In particular, we've changed what the image would be. Excellent point. I should emphasize that. Yeah.
It seems like the dimension of the image of L is 2.
Yes, absolutely, because that is a nice consequence here. What is the dimension of the image of L? Because a basis, there's lots of them, but a basis for the image of L is those two vectors, 2, -1, 1, and -1, -1, 1. That implies, which is two vectors, two vectors. We have a basis with two vectors. That means the image of L is two-dimensional. In this case, it would be a plane in 3D. We're building things with three-dimensional vectors, so we're going off in 3 dimensions, but we can only reach the span of two vectors, and so we're going to get a plane, a two-dimensional subspace of R3. Yeah. All right. Now there's the question, why does this work? Because, as was mentioned there is something a bit fishy going on. This matrix is not the same as the original. It's not. So why is it safe to do what we're doing? I'll illustrate this with a demo rather than doing a full proof on this. But remember, we've got 3 vectors to start with, say for this example here. I'm worried about one of them being a linear combination of the others. And it turns out in this case here that column 3, this one here, is this non-obvious combination of the other two. And let's just check that. C3 is -4, 1, -1. And -3C1 plus 2C2 is the same as -3, 2, -1, 1, plus 2, 1, -1, 1. That's -6 plus 2, 3 minus 2, -3 plus 2, which is in fact, yay, -4, 1, -1. So these are equal. All right. And so in our minds, that means I don't need that third column in a linearly independent set. because it's a linear combination of the first two. So if we were doing this without the RREF stuff, that would be our conclusion. But if we take a look at the RREF process for this, and you think about what we're doing as we do row operations here, what we just said is that whole column is this column here. If I take -3 times this plus 2 times this, I get the -4. That's like an equation. It's an equation that is always satisfied. This relationship is always true. And it's true for each of the rows. And as we do row operations, if I take 2 times this row and add it to this row, those ratios all stay the same as we do that, because the ratio is the same for each of these rows. When we add and subtract, we keep that ratio. Let's just do a quick confirmation that as we do our process to our REF here, we still get that same thing. Here our C3 is -1, -2, 1. And our other combination, -3, 1, 0, 1, plus 2, 1, -1, 1. That gives us -3 plus 2, -1, -2, -3 plus 2, -1. Oops. That was a -1. There we go. Phew. We found a mistake in my own copying error. There we go. No, it's not. What the hell? That's -1. There we go. Perfect. And so again, even after doing the row operations, the vectors changed, they point in different directions, but the relationship between that third column and the other two columns is the same. And we can, most importantly, check against the RREF version. The third column there is -3, 2, 0. And that one you can actually check pretty easily, because the first column is just a 1. We take it times -3. We're going to get the -3 in the first component. And then we add 2 times 0, 1, 0. We're going to get that equaling C3. So the chain of logic is this. We have a big messy matrix. Not my favorite, whatever. But we're looking for columns that are linearly independent. Fine. As we row reduce, we're going to have the same relationship between the columns. And so when we get down to this RREF, anything with a leading 1 is linearly independent of other things with leading 1s. Because again, this is a vector pointing in a fundamentally different direction than the other ones. They're those canonical basis vectors. Anything that doesn't have a leading 1 is a combination of the earlier vectors on the left. And so I don't need it. I don't need that vector if I'm trying to build a basis. I just need the ones that have the columns that have leading 1s in them. And then if the relationship wasn't changed as we did RAF, I can go back to my original matrix and make the same conclusion. This column here has the same relationship to these first two columns as these ones do. These two columns are linearly independent because these two columns are linearly independent. So all those relationships stay, even though the directions we're playing with, that does not stay the same as we go through RAF. The linear independence and combination relationships do stay the same. So going back to this whole process, what do we do here? We make our RREF, and then we look at the columns with leading 1s. Those define a set of vectors in the original matrix that will be linearly independent. That makes it fairly straightforward to do. RREF plus one more step. All right. So again, this is an algorithm. Learned how to do it. It's nice to have the understanding of kind of why it might be working, which is that last phase there. Any questions or comments about the process before we flip and go and do the kernel? Fantastic. All right, let's go do the kernel. So, scan. Yeah, we basically talked about that. All right. So the other space that's related to an image, or related to a transform rather, is the kernel. We have all the values that get mapped to the 0 vector in the output space through our transform L. This space here is the kernel of L. Another way to say that is that L of any vector equals the 0 vector in the output space. The kernel of L is equal to the set of all v's such that when I transform v, I get 0. This one's going to look more complicated, but it turns out not to be actually that bad in actual steps. It is longer than the image one. That is for sure, though. The plus side is that if we want to find a basis, so in other words, what's one building block vector or two or three building block vectors for this kernel? Well, the first thing we're going to do is put our matrix into our REF, just like we did for the image. So you can imagine a midterm or final question which is like, hey, find the basis for the image, find the basis for the kernel. Step one for both of them is get the row reduced echelon form, reduced row echelon form. All right, then we're going to do this other stuff. We'll get to that as we walk through it. So if we have the same matrix A, we're using the same matrix, we're going to, sorry, from 2 steps ago, we're going to use that same matrix. We have its REF already. And remember, the kernel is, this is equivalent to 1, 0, 0, 0 times x plus negative 3, 0, 0 times y plus 0, all the columns written out times w, z. All right. That's what it means to have this matrix. We imply that, yeah, we'd multiply these by some input to get the output. If we want the kernel, then what we want is that to equal a 0 vector. We want that. Well, that just means I want to solve this system. Oh, I want to solve a system of equations. And I want to solve a system of equations with a 0 on the right-hand side, because it's going to give me the x, y, z, w's that make the output 0. Well, wait, what is that? How do we do that? We know how to solve linear systems. We put the right-hand side as one of those separated augmented matrix things. So we're going to take this, and we're going to solve 1, 0, 0, minus 3, 0, 0, 0, 1, 0, 3, 4, 0. I want to solve that and find out which x, y, z, w's are going to give me a 0 output, because that's what it means to be in the kernel. Whatever inputs give me a 0 output. And that, we actually have a process for. I usually like circling the leading ones here. What we're going to do is we are going to build the solution bit by bit. We're going to write down the general solution in vector form. We did this once or twice, but it's been a little while, so let me just remind you how that worked. I think of the leading 1 variables, leading 1 columns, or variables as locked is the word that's coming to mind. That's locked in. Versus the other columns. The other columns represent free variables. All right. And let me show you how this plays out. So in this particular scenario with the variables I chose before, this is the x column, that's the y column, that's the z, that's the w. What we're going to do is add more letters, because we definitely needed more letters in this problem. We are going to let y, so the first column that doesn't have a leading 1, we're going to give it a variable that feels less spacey. We're going to call it s. And we're also going to let w equal another sort of parameterization type variable like t. S and t feel different than x, y, z, which feel like spatial variables. Once we do that, we can work through and find what a solution to the system looks like based on those variables. So let's play this out. We're going to go row by row. Row 3 tells me nothing, because it's all zeros. So row 3 tells me nothing. Row 2, though, let's do that down here. Row 2 says that z plus 4 w's equals 0. And we said, no, actually, we're going to call w, we're going to call that t. And so we have z equals negative 4t. And row 1 tells us that, I guess we can use it here. I can pretty much read this off with an extra 0 on the end. The row 1 says that x minus 3y plus 3w equals 0. We know we had a new name for w, we had a new name for y, and so x is equal to positive 3s minus 3t. when we move things to the right-hand side. So we're using the vector notation and then going back to, oh yeah, what do these represent? They represent multipliers for x, y, and z, and w, if we interpret it that way. Let me just pause there. Looking at this matrix here and getting to those two solutions by parsing out the two rows, is that okay for everyone? Feeling fairly confident? Fair enough. Please, questions, yeah. Pardon me? Why does this work? Let's get to the answer, and then we'll see if we can backtrack there. I think it'll make a little more sense when we have some tangible vectors. But yes, mostly because of the definition of the kernel. It's going to be my answer right now, which isn't very insightful. So please, yeah. Why are we switching to S and T? Again, I think it'll make sense when we get to the final answer. Yeah, totally reasonable question. Like, they're the same. Y and S are the same. So why bother? You'll see, I think, a little more clearly here. All right. That's great. So in fact, what we have is a full solution now. We have y equals s, we have w equals t, we have those two, we have this one, we have this one. Now I want to build the vector form of that. If I take the vector x, y, z, w, I can make it out of x was 3s minus 3t, y was s, z was minus 4t, w was t. So just literally putting the pieces together into a vertical stack in the right order. That's the key thing. But that is equal to a vector of 3, 1, 0, 0 times s plus, plus negative 3, 0, negative 4, 1, t. And that is the thing of beauty that we want. So let me just pause there. So one of the questions was why S and T? I think it's more clear here. If I take these two vectors, the S and T is how much of each of those two things, which is related to y, but not uniquely about y, so it's a different flavor. I think of S and T as how much of these two direction vectors we want to build with. So if we had, it would feel weird if this is y, because we have 3y equals, yeah, I don't want that. I want two vectors with something that feels different. Technically, it's a thing, though. So if you wanted to keep it y, that's actually true. The second thing is, what are we doing this for? So what we just solved, we solved for L of some x, y, z, w equals the 0 vector. That means that that vector x, y, z, w is in the kernel of L. Because the kernel of L is all things that map to 0. It's one of these things you just keep saying the same phrases over and over again. Well, that means that I have two vectors that transform to the 0 vector. Let's just check that. Let's confirm that. Let's just do L of that 3, 1, 0, 0 vector. That's going to be a flashback to what we did last week, so it's been a while. I'm just going to write out my matrix here and put the column vector here, 0, 0. And this is this row by column, row dot column dot product. That's how we actually do the implementation of our transform with a matrix. We take this collection here, which is x, y, z, w coefficients, and we multiply by x, y, and z, w values. And so when we do that here, we're going to get again, this times this gives us dot product minus 6, sorry, plus 6, minus 6, 0, oh, that's 0. And then we take the next column times that. We're going to get minus 3 plus 3. Oh, that's 0. Hey, it's this theme. Plus 3 minus 3. Hey, 0. That's the 0 vector in W. And so the vector 3, 1, 0, 0 is in the kernel of L. Let's do one more just to practice that skill. Hey, I think this vector's in the kernel. I bet you this vector is too, because of the way we built it. We solved a system of equations solving for what inputs give us 0 outputs. So here we go. If we also transform L of -3, 0, -4. This product's going to be a little longer just because there's more non-zero numbers in it, but that's fine. We take our matrix, 2, -6, -1, 2. -1, 3, -1, -7, 1, -3, 1, 7. Multiply it by -3, 0, 4, 1. And again, we do that dot product across this way, down that way. Whew, a little more complicated. -6 plus 0, -6 minus, sorry. That make oh, aha, we found an error. -4 is what is in the vector here. That's better. -6 plus 4 plus 2 gives us 0. Do the same thing again the next row. You get +3, 0, +3, +3, +4 is 7, -7 is 0. And last but not least, -3, -4 plus 7 is also 0. So again, if that row thing is not making sense, please, we can walk through that in more detail if you like as well. But it's the dot product of the coefficients with the x, y, z, w values. Let's do a quick check-in. Show of hands, the multiplication is fine. It's new, but it's fine. Okay. Okay. We're going to be using that a lot as we go forward, so it's good to have the foundation right now. So what, hey, oh my God, okay, sorry. All the leverage of the powers of the theorems that we did before come to play here. We just showed that this vector is in the kernel. We showed that this vector is in the kernel as well. Perfect. Wait, the kernel's a subspace. Isn't it nice to know some rules about subspaces? Absolutely. Any linear combination of those two vectors is going to be in the subspace too. So I don't have to take 3 of this and 2 of that. I know that that linear combination is also going to be in the kernel because it's closed under scalar multiplication and addition. All those things. Ah, so many properties. So this is going to be a basis for our kernel. Any answer that gives L of v equals 0, where's my definition here? Any v that gives me 0 when I run it through this function is what we solved for, right? We said, I would like to find all the solutions to the system, this matrix equals 0. We solved it by going into RREF. That's how we solve equations, systems of equations really easily. And we found our solutions. And we found specifically, these are the values that make the right-hand side 0. That means it's the kernel. That means this is the entire kernel right here. All the linear combinations of those two vectors. And so, poof, we can go a basis for the kernel of L. The things get wiped out and turned into zeros by our transform is the set, I forgot it already, 3, 1, 0, 0. Notice they're 4-dimensional vectors because the input's 4-dimensional and the kernel is an input space thing. And just like with the image, we have 2 vectors. And that implies that we have a kernel of L that is 2-dimensional. Or sometimes we write it as the dimension of the kernel of L equals 2, if we want to make it look equation-y. All right. So, let me pause when people are copying. So the 2 things from today so far is that we now have gone from, hey, what's the image? It's the places I can reach with my transform. What's the kernel? It's all the things in the input that get mapped down to that 1.0. We've gone that step further and gone, we can actually define what those spaces are built out of. Specifically, here we have a basis for the kernel. Every element in the kernel is going to be some linear combination of those 2 building block vectors. And we also found for the image a nice algorithm that said, how can we find, where's a good example? There we go. Up here, way up here, here we go. We can find an image for the outputs that we can get a basis for that, which is the minimal building block set that'll cover all the possible elements of the image with linear combinations, and we found that. So we can make it concrete now. Even better for us, honestly, is, I mean, this is fine. It's a nice midterm question, final exam question, but it's not that personally exciting. What is more interesting from a theory standpoint is a result we can generalize from this. So just taking a look back at, let's take a look back at the image thing for a second. Scroll, 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 image. Right. So in this case here, the algorithm for the image was take the columns with leading ones in the RREF. Those become your basis for your image. Leading column over the 1 becomes part of the image. For the other side of it, for the kernel, notice which variables became the free variables. The variables precisely without a leading one, the other columns. And so we have this natural selection. Each of the columns is either going to be one with a leading one, like these two, or it's going to be one without a leading one. Ones with leading ones get related to the image. Each one of them is going to lead to a basis vector for the image. Everything without a leading one led to, it wasn't these vectors, but it led to an S and a T that was a multiplier for some element of the kernel, some basis of the kernel. So we can split our dimensions up now, and we can get to what's about to be called the Rank-Nullity Theorem. So let's do this with a couple of stages here. So first off, how to look at one of these systems in full glory here. We hand you a matrix that, in this case here, is a 3 by 4 matrix. So 3 rows, 4 columns. With practice, you recognize, right, the columns are the output values. So the columns tell you the dimension of the output space. My output is spanned by these 4 3-element columns. I'm in R3 for the output. But because there's 4 columns, the input space is 4-dimensional. Because I can have this times x, that times y, that times z, that times w. I get 4 input variables that I would need, as we did with that matrix multiplication a couple of seconds ago. All right. Then the dimension of the image is equal to the number of columns in the RREF with leading ones. And that's equal to 2 here. So literally, if I just want the dimensionality, I don't care about the vectors, how many leading ones are in that system? 2. Okay, 2, great. I can read that off. Then the dimension of the kernel is going to equal the number of columns in the RREF without leading ones. Those were our free variables. Well, in that case here, that's this column and this column. Circle leading ones. So in this case here, that was 2. And so one vision of this process is that we started with 4 dimensions. We had vectors in R4, and then when we did this transform, we kept 2 dimensions. We ended up with 2 dimensions in the output. And you're like, I had 4 dimensions, now I only have 2. What happened to the other 2? The way I usually think of it is they got squished away. The kernel is things that get squished down to 0, dimensions that get squished down to a single point. So they kind of disappear dimension-wise. So we lost 2 dimensions in the kernel, and we have 2 dimensions left. We started with 4, lost 2. How many are left? 2 left. And that's going to apply in general because that algorithm is just based on looking at the columns in the reduced row echelon form. So if we have in general a, let's call it n by m, so m rows, m columns, we start off with m dimensions. That's the one we really care about. M dimensional input. And we go down to Rn. We're then going to have some row reduced echelon form. It's going to have some leading ones in it. And so that's going to be exactly like the last case. The number of leading ones is the dimension of the image. Sorry, leading ones in RREF. Let me do this. RREF. And the dimension of the kernel is going to be based on any columns, sorry, number of leading ones, let's say columns with leading ones. And the dimension of the kernel is going to be the number of columns without leading ones. In that RREF. Zoom back out here. And M, if we add these together, we're going to get M, which is equal to the number of columns. Because each of those columns fits one of those two categories. It has a leading one in it or it doesn't. And that, honestly, is the vanilla version that leads us to the Rank-Nullity Theorem, one of the fundamental theorems in linear algebra. If we have a linear transform, which has an n-dimensional input space, swapped it around this time, n-dimensional input space, that's all that matters. The output space didn't matter for any of the stuff we did. It was all about the input space. Then the number of dimensions in the input is going to equal the number of dimensions. That's just it, what we just said there. The input dimension is equal to the dimension of the image plus the image, dimension of the image plus the dimension of the kernel. That's what I'm saying. And sometimes we can give those two things a name. The rank is equal to the dimension of the image. And actually, more typically, it's used as the number of leading ones in RREF. We'll use the word rank later on to be how many leading ones do I have in this matrix? And the nullity is, as you'd expect, it's the dimension of the kernel of L. It's the things that get squished to nothing, to nullness. That's the nullity of this. And that's why this is called the Rank-Nullity Theorem. They're just new names for dimension of the image and dimension of the kernel. All right. So, things to know from today so far. How are you going to find a basis for the image? RREF, look for leading ones. How are you going to find a basis for the kernel? RREF, free variable, do some extra work. What does that lead us to? It leads us to this theorem that tells us if we have any kind of transform with n dimensions to start with, let's say we have a plane that gets squished down to the 0 vector in our output space. That's going to be one thing that happens. So the kernel is going to have a dimensionality. That's the kernel of L. And then, of course, the rest of the space gets mapped to somewhere else. That's going to have a dimensionality all of its own as well. That's going to be the image of L. And we have some guarantees about how those relate to one another. If we started off with 5 dimensions and 2 dimensions get squished down, 2 dimensions are in the kernel, there will be a 3-dimensional image. 2 plus 3 equals 5. We'll always have that relationship between the image, kernel, and the original input dimension.
Does this only work for real matrices?
This works for anything at all. The representation in terms of matrices, the phrasing here, sorry. The dimension, this theorem is true for everything. The challenge is we only have matrix forms for real vectors to real vectors. So the theorem applies, you could have polynomials as your 2 input and output spaces if you wanted, but we haven't talked about how you'd even represent that as a matrix yet. So for now, think of it just as Rn to Rm, yeah. We are only going to work with real matrices, yes. Yeah, because we could do other things, but there's an extra layer of hassle you don't need right now. Yeah. Alrighty, let's do one sort of consequence of this, several consequences of this. All right. So, consequences of the Rank-Nullity Theorem for function properties. All right. We talked about this last week, week before maybe. We had injective, L is injective, if and only if something. And it was something about images and kernels. bit of a deep dig right now. Anyone remember what that property that was equivalent to injective? One-to-oneness. Injective one-to-one. Yeah, please.
If and only if the kernel of L is only the zero vector in V.
Perfect. If and only if the kernel of L is only the zero vector in the input space. Perfect. Okay. Well, that now has an equivalency for us. This is the same as saying the kernel of L is zero-dimensional. Right? If there's only one point in your space, that's not a line. It's got 0 dimensions to it. There's no basis vectors, all that. But we just saw another equivalency for that today, which is the matrix for L, L's matrix, has, let's do it in 2 stages. The kernel has, so the L's matrix has no columns without leading ones. Right? Because every column that does not have a leading one is one dimension of my kernel. That's a long way of saying, with the double negative there, that all the columns of L have a leading one. Sorry, leading ones. And sorry, I should have put in RREF. I just kind of assumed that. But we do have to do the RREF stuff first. All right. If you think back to that earlier example, we had 2 columns. That gave us 2 vectors in the kernel that didn't have leading ones. Oh, well, we're not allowing that. If it's injective, we're done. We have to have every single column has a leading one when we row reduce it. All right, what was the other function thing that we looked at? Surjective, or onto. This was the covering the entire space out here. So whatever my input space was, when I map to L, L covers W. Oh, well wait, covering W, what's like an image way I could say that? I think we could say that that's the same as saying the image of L is equal to all of W. And another way to say that is that the dimension of the image of L is equal to the dimension of W. If I cover it all, they must have the same dimensionality. Let's see if there's anything else I'm going to say about that. Oh, yeah. Oh, wait, hold on. Let's go back a second here. If we have that, then the dimension of W is equal to the number of rows in our matrix. Right? Because if I have a 3-row matrix, my output's 3-dimensional. And that means that I'm going to have, this is the number of leading ones in our REF. And so putting these 2 things together, we're going to have every row in our REF has a leading one. All right. Now, we are always interested in functions that we can reverse, functions that we can invert, that we can process backwards if we need to. And one of the properties of that is that it has to be injective and surjective. That's the bijective combination thing. But notice what condition we ended up with. If we have something, a function, that is injective and surjective, it has every single column has a leading one in it, and every single row has a leading one in it. What kind of matrices might have that? Well, if we're going to have both of those, I think we're going to do it in a second, but I'm just going to put it here because it's fresh. If we want surjective plus injective, and that has a special name, not crucial for us, but bijective, means reversible, then we have to have leading ones in the RREF in every column and every row. And that means the RREF has to look like this: 1, 1, 1, 1, 0, 0, 0, 0. And actually, that gives the second consequence that the matrix must be square. The only way for that to work is to have the same number of rows and columns in our construction. If we snuck in an extra column, there would be a column without a leading one. If we stuck in an extra row, there would be a row without a leading one, to make them all match up. So one of the properties is that if we're going to have a surjective inversion function, it has to be a square matrix. And that's the same thing as saying the input and output dimensions must be the same. So a bunch of fun, deeper concepts are pulling out of that. And we are over time, so I apologize. I will stop there for today. If you have any questions about calculus or linear algebra, we'll stick around before your next class. But thank you very much.